Alright, let's look at the Doomsday and Extinction. Alright, so this is going to be a population model that is somewhat unstable. Alright, so we're going to assume that the birth rate is going to be proportional to the population, so some constant A times population P. And the death rate is going to be a constant rate, so I'm going to use B. Right? So if you plug into the general population equation, so beta is AP and delta is B, we're going to get this, right? So this is going to be equal to, so AP times P, so it's going to be AP squared minus BP, right? Then what I'm going to do is I'm going to actually factor out AP. So I'm going to pull out the AP. Then you're going to have a P minus A, pull out the A and P. So it's going to be B over A. Right? To make it look very similar to a logistic equation, I'm going to use K for this guy. So A is actually K. And I'm going to use M for B over A. So here, this is M. Right, so the equation looks like this. So it's going to be K times P, M, actually not M, it's actually P minus M, right? So if you compare with the logistic equation looks like this. So it's a dP over dt is equal to K times P. Then here's the difference. It's just a negative of what we have here. So M minus P instead of P minus M, right? So this is actually a negative version of the logistic equation. So only difference is if you rewrite it as, say, I'm going to pull out the negative sign. So if you write it as a negative K, P times the quantity M minus P, which means that this is a logistic equation with K replaced by negative K, right? So the solution, the population function is going to look like that. And you notice that here, there is no negative sign here, right? For the logistic equation, you have a negative sign. All right. So let's look at this example. You see why I said that this population model is unstable. All right. Oh, by the way, there's a name for this M right here, right? So this M is actually called the threshold population, as opposed to carrying capacity for logistic equation. So this is called threshold population. All right. So let's. It's probably the easiest to look at the concrete example, right? So let's just do a simple example. dP over dt is equal to K is equal to 1, P times quantity P minus 5. So M is equal to 5. So the threshold population is 5. All right. So let's actually look at the GeoGebra here. All right. So open up GeoGebra. All right. I actually already drew the slope field for this particular differential equation, right? And threshold is 5, so I can actually put y equals 5 and hit enter. Right? This is a threshold, right? Then interesting happens. So this is going to be a case for Doomsday, right? Let's just say initial population is greater than the threshold population. So we set the initial population to 6, and what happens is this, right? Oh, actually, this is not what I wanted to do. Here, right? So what I wanted to do is here. So let's try to solve ODE, right? initial population is 0,6, and it's going to look like this. Right, so maybe I'll just stretch it out a little bit. So it's an interesting thing happened here. So here, this is a solution. So this is the initial population. As time goes by, you can see that the population experiences kind of explosion, right? It actually, this denominator, so this is a solution, denominator actually becomes 0 when t equals natural log of 6/5. So the population actually explodes to positive infinity at some point. And so that time is called the doomsday, because population just explode to infinity, right? So t equals natural log of 6/5, just solving this denominator equal to 0 for t. That's called doomsday, and you can see that the population just explodes, right? So if you have initial population greater than threshold population, you're going to have a doomsday, so population explosion. All right. On the other hand, if you have initial population smaller than 5, so let's just say 4, and then we compute it, right? Now the solution looks a little bit different, and you can see that here, right? So this is initial population, right, below the threshold population. You can see that the population is going to decrease, actually heads toward 0, which leads to extinction, right? So when you have a case like that, and the equation like that, if the initial population is greater than this threshold population, it's going to lead to explosion of a population. So that's called the doomsday, right? Extinction, it's going to go, it's going to steadily decline to eventually 0, and it goes to extinction when the population, initial population, is below the threshold, right? So you can see that here, right? So this is the equation. As instead of t, I use x. It goes x gets larger and larger. Denominator gets larger and larger and larger, so that the population goes to 0. So eventually, it leads to an extinction. Right. So if you have an equation like that, and m is called the threshold population, it's just a negative version of the logistic equation. But this population model is very unstable. And the only way you can have a steady population is that you start at the threshold population, then the population stays the same all the way through. But if you have too many to begin with, it's going to lead to doomsday. And if you have too few to begin with, it's going to lead to extinction. So you can see that here. So the population here, I think it came out to be, I forgot what it was. So if you start with population 6, right, then the equation is this. So negative 30 over 5x minus 6. So you have negative 30 over e to the 5x minus 6, and the doomsday is going to be, you can just set the denominator equal to 0, then you're going to have an explosion of population. So t is equal to, if you solve it, it's a natural log of 6/5, and this is called doomsday, right? But if you have initial population full below the threshold population, what happens is that the function is going to become like this. So let's start with 4, right? Then you have a 20 over 5, e to the 5x plus 4. So you have population function is 20 over e to the 5x minus 4. Actually, was it plus 4? Plus 4, sorry. Plus 4. And as you can see that if you look at the limit of the population function as t approaches infinity, and you can see that the denominator actually goes to infinity, because e to the big number is a big number, plus 4 is still a big number. So 20 divided by a really big number approaches 0. So this limit of the population is equal to 0, and this is called the extinction. Right? So this is the Doomsday and Extinction. If you have too many to begin with, it leads to Doomsday. If you have too few to begin with, it leads to an extinction. Right? That's it. I hope that this was clear.